Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where we are discussing every chapter topic wise. Also we are discussing previous year questions from that chapter. So today here I am with discussing magnetism and matter chapters previous year questions and their answers. So we have already completed magnetism and matter chapter. If you have not seen this chapter, you can check in the playlist given in the description. Also all the chapters before magnetism and matter, all the 5 chapters including magnetism and matter are completed, and this week's KPL, that is a big announcement for today, that this week's KPL coming on Sunday will be based on moving charges and magnetism and matter. So whatever we are going to do tomorrow and till Saturday, that parts will be covered in our next week's KPL, not upcoming KPL. In upcoming KPL only moving charges and magnetism and matter, these 2 chapters will be covered. We have already taken care of moving charges and magnetism in somewhat in our previous KPL, but this is a very important chapter, so we are continuing with moving charges and magnetism as well as magnetism and matter. Yes, question paper is finalized, so that's why I am giving you the update. Now before moving on, if you want to get all the update related to our KCET 2025 releases, do join our WhatsApp channel. Here you will get all the updates, all the videos that we are doing in our channel. Now let's move on to the questions. First question: the Curie temperature of cobalt and iron are 400 Kelvin and 1000 Kelvin respectively. At T is equal to 1600 Kelvin, the ratio of magnetic susceptibility of cobalt to that of iron is. Now this part, Curie temperature, is no longer part of your syllabus, but there is a relationship between Curie temperature and magnetic susceptibility. Maybe this formula can come in your JEE exam, so that's why I am solving this. Don't worry, even if they are saying this is deleted, maybe some questions sometimes overflow into this and comes, so be prepared if this question comes. The formula is magnetic susceptibility is equals to, there is a constant, C is a constant, okay, divided by T, that is the temperature, minus Curie temperature. Okay, now for cobalt we can write chi cobalt. It's the symbol is like X and these arms are little bit twisted. So for cobalt it is constant C divided by temperature is 1600 and Curie temperature for cobalt is 1400, right? So it is C by 200, right? Now chi for iron, let me write Fe, C by same temperature but Curie temperature is different, so it is 1000, so it will be C by 600, right? Now they have asked you to find the ratio of susceptibility of cobalt to that of iron. So what you have to find? You have to find chi cobalt divided by chi iron, right? So it will be C by 200 divided by C by 600. So 600 will go up and 200 will come down, so it will be 3. So the ratio is 3. Okay, so correct answer is option A. Very simple question if you consider the only formula that you have to use, but the property is no longer part of the syllabus. So what to do? The horizontal component of Earth's magnetic field at a place is 3 times 10 to the power of minus 5 Tesla. If the dip at that place is 45 degree, the resultant magnetic field at that place is. Okay, so if the magnetic field dip is this angle, okay, now this is the vertical field, this is the horizontal angle, okay, and the dip angle is this. The dip angle is this theta. Now this is also a part of deleted syllabus. Okay, so if this is B, okay, this is horizontal component, okay, this is vertical component, okay, but we know that horizontal component from this vector diagram we can write horizontal component is basically b cos theta. Okay, so b should be bh divided by cos theta, right? Now bh is given by 3 times 10 to the power of minus 5 Tesla, so b should be 3 times 10 to the power of minus 5 divided by cos theta, cos 45, that is 3 times 10 to the power of minus 5 divided by root 2, sorry, 1 by root 2, cos theta is 1 by root 2, cos 45, so it will be 3 root 2 times 10 to the power of minus 5. So 3 root 2 times 10 to the power of minus 5 Tesla, so this is the answer. Now let's move on. Which of the following statement proves that Earth has a magnetic field? Very important question. It is relevant, it is not deleted. So the Earth is surrounded by ionosphere. Obviously not. The intensity of cosmic rays stream of charged particle is more as the poles at the poles than at the equator. Okay, so magnetic field strength, the poles, this is the proof that they have charged particles are moving in a magnetic field. They tend to move towards the poles. So basically you can say that poles, there are 2 magnetic poles. So basically that proves that Earth is a magnet. Okay, Earth, the magnetism of Earth entirely is deleted, but the properties are still there. You have learned that in first part of the book. So it is in the syllabus. Don't consider this as out of the syllabus. Earth's magnetic field always has a horizontal component except at, this is now deleted. Okay, this is magnetic poles. Everywhere else they have a horizontal component. Okay, obviously the question is very straightforward, either poles or equator, but equator they have horizontal component. So only place that they don't have any horizontal component is magnetic poles. Now question number 5. A paramagnetic sample shows a net magnetization of 8 ampere per meter when placed in an external magnetic field of 0.6 Tesla at a temperature of 4 Kelvin. When the same sample is placed in an external magnetic field of 0.2 Tesla at a temperature of 16 Kelvin, okay, the magnetization will be now this part is also partly deleted, but you should know that net magnetization and the magnetic field, the relationship between magnetization, magnetic field and temperature is given by magnetization is equals to Cb divided by temperature. Okay, so for say substance 1, initially it was M1 and for final is M2, right? So if you divide them you will get M2 by M1. We are trying to find M2. M1 is given, so we are writing it like this. We can write this as Cb2 by T2 divided by Cb1 by T1. So this T1 will go up and C cancels. So B2 T1 divided by B1 T2. Simple formula, right? Now let's put the values. M2 is given as M2 we are trying to find. M1 is given 8, right? 8 ampere per meter. Okay, now B2 is given, B2 is 0.2 Tesla. T1 is given 4K, right? And B1 is given 0.6 Tesla and final temperature T2 is 16K, right? So 4 4s are 16. Okay, now M2 will be, let's take this 8 in this side, 8 times, you can remove the decimals, so 2 divided by 6 times 4, 4 4 2 4s are 8, 3, so it will be 2 by 3. So M2 is 2 by 3, right? So 2 by 3 is the correct answer. Now let's move on. the ratio of magnetic field at the center of a current carrying circular coil to its magnetic moment is x. If the current and the radius both are doubled, then the new ratio will become. Now magnetic field, we know that magnetic field at the center of the coil is given by, I have wrote that formula multiple times, mu naught I divided by 2r, right? So this is the formula, and the magnetic moment is given by pi r square I. Okay, now if you divide them, the ratio initially B by let me write it capital M. Okay, don't get confused, because see, the only problem in this chapter is they write magnetic intensity also by magnetization as capital M, also magnetic dipole moment as capital M. So in magnetization generally represented by I, capital I. Now capital I is sometimes confused between current, so that's why it is a little bit confusing. So they are actually out of symbols for this chapter. Now if you do this, you will get I cancels, mu naught by 2 pi r square times r, so r cube. Okay, so I cancels. Now initially this value is given as x. Okay, now what they have said, they have increased the radius as well as current. Now you can see there is no effect of current remaining in this formula. So final value b dash by m dash, okay, equals to mu naught will remain constant, obviously 2 pi is a constant, only thing that will change is r, so that will become cube, so it will become 1 by 8 mu naught by 2 pi r cube, right? 2 r whole cube means 8 r cube, so I have taken the 8 outside. Now this is x, this is x, so it will be x by 8. So the correct answer is x by 8, right? Now let's move on to the next problem. In a permanent magnet at room temperature, domains are partially aligned, domains are all perfectly aligned, magnetic moment of each molecule is 0, the individual molecules have non-zero magnetic moment which all are perfectly aligned. Now you should remember that domains cannot perfectly align because domains consists of atoms or molecules. Now they are at constant vibration in the presence of temperature, right? At temperature they are always vibrating. We have learned that. Now only this vibration stops at absolute zero, right? Other than absolute zero, they are always vibrating. Now since they are always vibrating, that means all the domains cannot perfectly align. There will be some mismatch, only partially they can align. Okay, now since it's a permanent magnet, so there has to be some sort of alignment. Okay, because it's a permanent magnet, some domains should align according to the north pole and south pole, and that's why domains are partially aligned. They cannot be perfectly aligned. If they are perfectly aligned, that means it's a perfect magnet, which is not possible obviously, as the atoms are vibrating. Now let's move on. Needles N1, N2 and N3 are made up of ferromagnetic, a paramagnetic and a diamagnetic substance respectively. Okay, a magnet when brought close to them. So N1 is, let us identify them one by one, that will be helpful. N1 is ferro, okay, N2 is para and N3 is dia. Don't get confused, write it down. You have enough time. This is only small thing that you are writing. Okay, now they have said what will happen to a magnet. Now if you brought a magnet, ferromagnetic substance will be attracted, paramagnetic substance will be attracted but weakly, okay, and they will be repelled. They will be attracted, they will be attracted but by small amount, but they will be repelled. So let's see the options one by one. They will be repelled, so repel sign I am giving in this direction. Okay, attract N1 strongly, attract all three of them obviously wrong. Okay, attract N1 strongly, correct, N2 weakly and repel N3 weakly. So this is the correct option. Okay, now if you can check the other options, attract N1 strongly, correct, but repel N2 and N3 incorrect. Okay, attract N1 and N2 strongly but repel N3, that is also incorrect. So only correct option is option B. Okay, now let's move on. The strength of the Earth's magnetic field is constant everywhere, zero everywhere, having very high value, varying from place to place on the Earth's surface. This is a very easy question. Okay, so this chapter, this earth magnetic field used to be a easy part, but now it is no longer part of the syllabus, but this question may still come. Okay, coercivity of magnet where the magnet ferromagnet gets completely demagnetized is 3 times 10 to the power of 3 ampere per meter. Now here coercivity is basically the magnetic intensity. Okay, coercivity is nothing but magnetic intensity. Okay, that is magnetic intensity required to demagnetize a magnet. They might, though coercivity is no longer part of the syllabus, but they might ask this question in a different format, that the magnetic intensity required to demagnetize a magnet completely is given by 3 times 10 to the power of 3 ampere per meter. Okay, so they have instead of using the term coercivity, they have changed it to the term that magnetic intensity required. Okay, now the minimum current required to be passed in a solenoid having 1000 turns per meter, so that the magnet gets completely demagnetized. So what you have to do, that you have to use the formula that inside a solenoid the magnetic intensity that can be developed is Ni. If you remember the class, yesterday's class, where we have discussed magnetic intensity is basically H equals to B by mu. Okay, B is mu Ni. Okay, when there is some material involved inside it, right? So B by mu is Ni, right? So what we have to do, we have to find the magnetic intensity. Okay, H is basically given and N is given 1000, and you have to find the current. Okay, that is equals to 3 times 10 to the power of 3. So I is basically 3 ampere. Okay, this is 10 to the power 3, this is 10 to the power 3, so they will cancel. So I is 3 amperes. Okay, simple question, simple answer. Okay, even though this term coercivity is no longer part of the syllabus, this question still might come in a different form. Similar question, not the same question, but similar question still might come, so be prepared. Now let's move on. Next question, the susceptibility of a ferromagnetic substance is. What is the susceptibility of a ferromagnetic substance? It is very greater than 1. Okay, susceptibility of ferromagnetic substance is very greater than 1. For paramagnet is just greater than 1. For diamagnet is just less than 1. Okay, the magnetic dipole of a magnetic dipole of magnetic moment 6 times 10 to the power of minus 2 ampere meter square and moment of inertia 12 10 to the power minus 6 kg per meter square performs oscillations in a magnetic field of 2 times 10 to the power of minus 2 Tesla. The time taken by dipole to complete 20 oscillations. So time taken by dipole to complete 20 oscillations is basically, first of all, you have to calculate the time period. The formula I have given you, I by mb. Okay, so 2 pi, you need to remember this formula. This is a very simple and easy formula. I is given by 12 times 10 to the power of minus 6, right? Here I is moment of inertia. This is not current. Okay, many students write this as current. Now what is M? M is magnetic field. Sorry, M is the magnetic moment. 6 times 10 to the power of minus 2 times oscillations in a magnetic field is 2 times 10 to the power of minus 2, right? So what we will be doing, 2 pi minus 6 divided by 12, 6 to the 12 times 10 to the power of minus 4, right? So this 12 will cancel. So the time period will be 2 pi square root of 10 to the power of minus 2 minus 6 by minus 4. So it will be minus 2, or 2 pi times 10 to the power of minus 1. Okay, square root means the power becomes half, right? So now this is for one oscillation. This is the time for one oscillation. So for 20 oscillations, obviously for 20 oscillation, time required will be 20t, that is 20 times 2 pi times 10 to the power of minus 1. Now 20 times 10 to the power of minus 1 means 2. So 2 2 is a 4, 4 pi. Okay, this 0 and this 10 to the power minus 1 will cancel. So 4 pi. Now what is 4 pi? 4 times 3.14. So it is roughly equals to 12 seconds. If you check the answer, 12 seconds is given. Okay, no need to worry. Okay, 12 is directly given. If some decimals are given after 12, then you can take in that as well. Now, which of the following properties is false for a bar magnet? It does not produce magnetic field. Obviously, this is false. The bar magnet does produce a magnetic field. Let us check the other options. Its poles cannot be separated. Correct statement. Not incorrect. It points north-south direction when suspended. Correct statement. Its like poles repel and unlike poles attract, which is also correct statement. So correct, incorrect statement which is that you have to select is option number A. Okay, now question number 14. X1 and X2 are susceptibilities of a paramagnetic substance at temperature T1 Kelvin and T2 Kelvin respectively. Then now this is also no longer part of the syllabus, but still I am solving it. Susceptibility X1, it's not X1, it should be chi1. Okay, chi1 is basically any constant divided by the temperature. Now this is below, because paramagnetic substances are above QD temperature. So above QD temperature, that formula that we have learned in the first question does not valid any longer. So only the thing is it changes with inversely proportional to the temperature. Okay, so chi1 T1 is constant. So we can write that chi1 T1 is equal to chi2 T2. Okay, so this is the correct option. At certain place, the horizontal component of Earth's magnetic field is 3.0 Gauss and the angle of dip at that place is 30 degree. The magnetic field of the Earth at that location. Same question we have solved. So this was one of the patent question appearing multiple times. So theta was here, magnetic field is here, and horizontal component. Now Gauss is no longer used, only we use Tesla. Okay, Gauss is CGS unit, and Tesla is, because Tesla appears to be 10 to the minus 5 minus 6, so that's why Gauss was used, but Gauss is no longer used. So B is basically BH by cos theta. Angle is given 30 degrees. BH is given 3. So cos 30 is root 3 by 2. So it will be 3 times 2 divided by root 3. So it will be 2 root 3, right? So 2 root 3 means 2 times 1.7 almost equals to 3.5. Okay, so 3.5 Gauss is the correct answer. Now let's move on. Core of electromagnets are made up of ferromagnetic material which has high permeability, high retentivity, low permeability, low retentivity, high permeability and low retentivity. This is the answer. This term retentivity is hysteresis etc. is no longer part of the syllabus, but permeability part of the syllabus. We know that higher the permeability you need less current to create a higher magnetic field. We have solved one numerical based on that. So this is still part of the syllabus, but retentivity is no longer part of the syllabus. Okay, if there is a torsion on the suspension thread, no torsion in the suspension thread, then the time period of the magnet, I have solved this already. Everything is I here, not 1. Okay, and we know that the correct formula is T is equal to 2 pi I by mb. The magnetic susceptibility of a paramagnetic material at minus 73 degrees Celsius is 0.0075 and its value of, again this is no longer part of the syllabus, but since we have already used the formula chi is equals to C by T, right? Now at temperature 1 it is T1. So what is the temperature? First temperature is minus 73 degree. So minus 73 degrees Celsius, T1 will be 273 minus 73. Okay, so only thing is that you need to consider is this. Okay, and the final temperature T2 is 273 minus 173, that is 100 Kelvin. So the question was given to check if you can change the units. Okay, so chi1 T1 is equal to chi2 T2. Okay, chi1 is given as 0.0075 T1 is 200, chi2 we are trying to find, T2 is 100. So let's cancel this. Okay, so chi2 is basically 0.015. Okay, so 0.015 is the correct answer. So these are all the previous year questions from this chapter. We have completed all the previous year question from this chapter. And sorry, one more question is there. A susceptibility of a certain magnetic material is 400. What is the class of the magnetic material? Obviously it's a ferromagnetic material. Okay, susceptibility more than 1, very more than 1 means it's a ferromagnetic material, and close to 1 means it can be diamagnetic or paramagnetic based on how big it is. Okay, ferroelectric, they have given option ferroelectric, which does not exist. So we have reached at the end of the lecture today, and this is a very small chapter, so we have completed all the previous year questions, but mostly 2 questions. If you see last 10 years 19 questions came, so almost every year 2 questions coming from this chapter. So we have completed this chapter, and next we will start with electromagnetic induction tomorrow. So if you have not watched the theory parts, you can go back and check the theory questions. Also I have given 2 homework questions. Try and solve those 2 questions from yesterday's lecture, and please share with your friends and subscribe to our channel. Thank you for watching.